One more minute and we'll get started. Okay, let's get started. Hey everyone, thank you for attending today's data ops session, and we'll be talking about the MLOps journey that Habib and Neil from Spark New Zealand will be presenting on the experience in deploying MLOps within the business itself. Before we sort of get started and intros, I just wanted to do a quick review of data ops as we do per every meetup. Neil, do you mind going back to the first slide? I just quickly go through what data ops is. And it will be good to get Habib and Neil, your perspective of how data ops and ML ops fits into it after the presentation or during the presentation. But at a very high level, guys, data ops, there is a very long explanation for it, but it's really to increase velocity to deliver sustained value with data products. And I call it products because it has the ability to automate your entire architecture and your data architecture wrapped around it. And really, it's the ability for data engineering, data science, and DevOps to come together and work together on single projects. And it's really that collaboration mindset. And it's all about simplicity, automation, and delivering things in smaller chunks to the business and making sure the business is engaged through that whole process. That's what data ops is at a very high level. We're not going to go through it beyond that. Now, I'm going to do a quick intro for Habib and Neil, and you guys are welcome to add to it, Habib and Neil. Neil is a senior data scientist at Spark New Zealand. He's worked in various data and software roles across startups, telcos, and IT sectors. He's completed a PhD in AI machine learning in 2018. Pretty much interested in anything with data, automation, and AI. And he's passionate about creating data-driven, scalable, intelligent digital assets. Habib, I've known Habib for about 4 or 5 years now already in New Zealand, and Habib is the chapter lead in the data science at Spark New Zealand, a history of working in telecommunication industry, has a strong engineering background and PhD in medical imaging in University of Oxford, and he focuses on adapting business strategy with data science and AI, which is, I think, the role that he's focusing on. One of the things with just Habib, me and Habib, we've got similar thinking. When I came across Habib about 3 or 4 years ago, he had we both picked up similar challenges in the data industry around data engineering and data scientists, and we hit it off in terms of conversations and just in terms of topics around data engineering, data science, and data ops and ML ops over that period of time. So with that, I'm actually going to hand it over to Neil to start the presentation.
Thank you, Akash. Thank you for the great introduction. I wouldn't have been able to introduce myself as good as you did. Let's get started. And I think, let me just set things up a bit. Yep, that's the right one. I hope you can see my pointer.
Yep.
Nice. What we have planned to do today is kind of move through a few different topics that are quite related to machine learning operations. So machine learning operations is, we see machine learning operations as one of the most important component that should exist in enterprises or organizations that are trying to scale their data science capability. But overall, we see that data science lifecycle management is the bigger picture that we would like to look into. So today we are going to talk about a bit of motivation, and then talk a bit about the data science lifecycle management as a whole, and then go into machine learning operations and what are the different maturity stages that are there in machine learning operations. We are also going to touch upon a bit about analytics and governance and the need for quality control in big enterprises where you have lots of machine learning systems running in production, and how it is extremely important to create a governance layer around it. And then we are going to touch upon how we are enabling data science lifecycle management in Spark New Zealand, and probably be able to have some time for some demonstration on some of the tools that are available for us to apply in regards to machine learning operations and data science. So first of all, I will hand it over to Habib to talk a bit about our data science practice in Spark, and a bit of detail around key phases of data science projects.
Thanks, Neil. Can everybody hear me clearly? I'm assuming a yes, if nobody's
Yep.
complaining. Yeah. So I'll just start with a small story. So what happened was I joined Spark in early 2019 as a senior data scientist over there. And at that time, we had 3 or 4 models which were say, churning out results, machine learning models, and it was quite early. It were quite early phases of machine learning over at Spark. But what we slowly noticed was that this was accelerating quite quickly. So once you start seeing the results of those models, people start demanding more and more. And it was a big challenge for us to actually try and bring more people who can do the work, manage the technology, and also create the processes around this as well. Now, why do we want data science in Spark? Now, and what do we define as a practice as for data science in Spark? One of the important parts is that we want to create and operationalize these data science assets to give continuous value to the organization, not just one time, a continuous value. And in order to do that, we have to find the sweet spot, as you see in the center, where people, technology, and processes, all of them work together and give you an ultimate result at the end. Because that's where you can scale, you can innovate, and you can automate all of that over and create a continuous value for the organization. Now, this can only happen if we try to understand the machine learning life cycle and then try to deliver according to that. Okay. Now, if you move on to the next slide, Neil. Now, what if we have to try and understand what are the key phases of a data science project? Now, there are 3 important phases: prototyping, substantiation, and operationalization. Now, that was given by a Rapid Miner. What they noticed was that prototyping is the phase which we all go through, and most models will go through, or 100% of the models will go through that, where you try to understand, explore the data, prep it up, and build some initial model candidates. And most projects go through that. When you move on to the next phase, which is the substantiation phase, only 30% of them survive over there. Because here in that case, what you're trying to do is you're trying to find the best candidates that have been trained, tested, and more data is needed to validate them or not, or do we have enough data or not for that? And if you move on to the operationalization phase, only 1% of them survive up to that. That's because in this between substantiation and operationalization, many of those models will actually would say phase out because either they are not giving relevant results, or would say they can't be automated, or would say they can't be they're taking too long for development and so on. And this is less than 1% of it, which is a big concern for us. Now, if you look at the bottom of the tools, what is our focus on tools and teams, and how are we delivering value for business? If you look at that, prototyping is very much focused on tools and teams. There is no talk about value for business over there, or very less contribution over there. The value for business only takes on the operational side, where would say it's actually in deployment and it delivering value. Now, as an organization, what we wanted was how could we get a balance between that? And how can we actually make this streamline much more organized so that we can start getting some value for the business in the initial parts itself as well, and reduce the focus on tools and teams so that we can do things much more faster and scale it up in a much more higher way. Now, in order to do that, we have to understand the ML life cycle and try to introduce some MLOps across that. Now I will hand it over to Neil to take you through the rest of the presentation and explain what are the different stages of an MLOps lifecycle.
Thanks, Abib. Yeah, nice one. So something quite related to the key phases of data science project are the people who are involved in these different parts of the data science project. And typically what we have observed is the general notion in the organization is data scientists are the only roles that exist who does things end to end, and everything from prototyping, substantiation to operationalization, everything can be done by data scientists. Now, here's a slide that can make or break my relationship with my data scientist friend. And I would try to introduce our kind of people, and I am included within that. And it's a pity that you can't hear the sound, but I will play the video anyway to start it off. Is it? Ooh. I don't think the video is working. Yeah. It's probably not a video anymore, but it would have been great if I could have played that video. But what that video actually shows us in a very funny fashion is that how we actually really love open source technologies. So as data scientists, we are really interested in technologies that are open source because of a particular reason. One is that in open source technology allows us to move really quickly in terms of research that happens in data science and how that gets implemented into product. Because in a commercial environment, it takes so many years for latest technology to be available as a commercial product, where open source technologies really kind of helps us to be quicker. And the other thing that open source technology does is that allows us so much more flexibility in terms of what we can do. So we have a much larger degrees of freedom in terms of the experimentations that we want to do in an open source environment, where in a commercial environment, things are much more standardized than in an open source environment. Something else that data scientists really like is what we call as experimentation. And experimentation is nothing but you take some data and you put it into a pot of linear algebra and you kind of iterate over it many times, and out comes a model. When you do lots of experiments, because you have such higher degrees of freedom, it gives you lots of capability of experimentation. But with great experimentation, someone had said, with great flexibility comes a great mess. Now, what do I mean by with great flexibility comes a great mess? Now, if we look into the experimentation loop that we go into when we develop a particular data science product, and this is where it's very different from your traditional software-based product as well. Here, it includes experimentation. But what happens with experimentation? What you see with experimentation is that over time, as you experiment more and more, the reproducibility capability goes down exponentially. Second thing that you notice is as you do more and more experiments, your technical debt keeps on increasing, because at the end, when you want to deploy a particular experiment into production, you have to do a lot of technical changes, which you did not do because you took a quick path towards doing an experimentation. And the third thing that you notice with experimentation is the performance that you're expecting. So the reason why you are experimenting is because you want to come up with the most optimal model or the most optimal data science product. And optimality is kind of increases a lot initially, but then it shows a saturation characteristic, and more experiments does not necessarily mean you will get a lot of performance uplift out of it. Now, when you look into these kind of characteristics, you can already realize there is a requirement of life cycle management, because now the data science product during development or during operationalization, the lifetime is quite high, right? So when you are developing, you're kind of doing an initial development, but when it goes into operationalization, organizations are using it as an asset, and it stays as an asset for a long time in an organization, and it requires management. Now, this is what we were taught when we were in the university about what data science life cycle process looks like. Right. So if we go back to the kind of classic crisp DM kind of a setup, it told us that data science life cycle process starts with business understanding, and then you have to do data understanding, and then you go into data preparation, modeling, evaluation, you deploy it, and you iterate over it. Now, the interesting thing is that this, when you actually try to implement this particular life cycle, you realize that it hides a lot of fact that you see in a environment where a lot of people trying to collaborate together and trying to build data science product, and they're trying to accelerate the data science capabilities in the organizations. Now, one of the most important thing is collaboration that comes with it, and the variety of role that are involved in this particular life cycle, right? So when we were taught about this life cycle, we were never told that at each of these individual step of business understanding, data preparation, and modeling, there would be multiple roles that would be interested in this particular category of the life cycle, and there needs to be more than one people who needs to come in and each of these stages for it to be successful. For example, in business understanding, you would want business analysts and data scientists and data engineers to come together to understand the business. You would also want to involve, for example, product owners or application specialists, who are the people who are actually bringing that business problem in. In the data understanding, of course, you would, like data engineers would be the most important people who would go into the exploration phase of where is data, how do I collect it, how do I extract it, and so on. Data preparation is a place where both data scientists and data engineers would come together to kind of decide how data needs to be prepared. During the modeling phase, it would be mostly data scientists who builds the model, but data engineers will of course be supporting them with the right data. And evaluation is of course, like data scientists are quite capable of doing that. And when it comes to deployment, it is mostly the operations people who might be machine learning engineers, or it might be data scientists who will come together in terms of doing that. Now, in a large organization like ours, we have many people who comes together in terms of doing this, and we have variety of roles that collaborates together, and it tells us nothing about how do you collaborate in these kind of scenario. Now, the second important thing that it does not tells us is about the governance and the reproducibility that is required for data science product to be successful. Now, our data science products are so close to the customers because it's completely automated, and it goes out to it's just one step away from reaching out to the customers. Um, the great thing of data science being an automated product is it is very close to the customer, but then there is a risk factor of that as well. If there is something that goes wrong, or if it is biased in a certain way, we know what happens, right? And then governance in terms of how data science products are built becomes extremely important, and reproducibility is of course part of that. So if you have reproducibility, things can be governed. Now, the third important thing is something like asset management. So by asset, what I mean is that in a typical machine learning scenario, data science project, your asset is more than just the code. So you have data assets, you have code assets, you have model assets, you have application assets, and each of these assets requires its own management mechanism, which is not always exists in all the data science setup or organizations. One of the most interesting characteristic is that in machine learning scenario, you have asset degradation, which is very interesting. So model is one of the asset which degrades over time. And which is a very typical characteristic of your data science life cycle process, and it requires certain kind of attention. And the last thing is, of course, trust and adoption is extremely important. And when I talk about trust, it is about business being able to trust the models or the data science product that we build and how they're adopting. And it, in terms of adoption, we can go into greater detail around. There are different kinds of adoptions that exist in an organization. And right now, I'm not going too much into this detail, but that's really important. Uh, Now, coming into the development of data science lifecycle, so that the development phase that we go into in terms of data science lifecycle management. So if you think about the last slide, if we think that we have done business understanding and we have some form of data understanding, and now we are ready for development, um, to me, it is not a linear loop. There are multiple loops that are, I mean, like that sits within that bigger loop that you saw in the crisp DM setup. Now to me, a great definition of a loop is something that has a clear goal and a tangible deliverable. So if I have to define these three loops that I am presenting here, so the first loop is the data loop. So where um, data engineers are first of all sourcing data, blending data, and then they're doing data engineering. It of course involves feature engineering and feature selection, where you are going into data and engineering certain features from some of the existing data. You are selecting features automatically or manually, and you are also doing some form of exploratory data analysis to understand the data. Now, the interesting thing is that one of the key deliverables of this particular loop is that data should be ready for consumption. So the deliverable of this loop is data that is ready for consumption for training to happen on top of it. Um, and this is where the handoff happens in terms of model loop. So once data is ready for consumption for the model, then it comes into the model loop where you have mainly model selection, parameter optimization, and model evaluation. These are looped across where you are testing out different algorithms, machine learning algorithms, and several hyperparameter versions of those models, and you are having some form of evaluation mechanism with which you are evaluating and kind of creating a ranked order of the best models. And in a lot of cases, automated machine learning has taken over this whole loop where you can do the model selection and parameter optimization as a single step with a model evaluation as part of it. Now, the main goal or the deliverable of the model loop is to be able to create a model asset, and this model asset is can be in form of an object or a serialized object, or it can be in form of an application where you kind of wrap around a model object with an API endpoint, and it is ready for serving. And then comes the operations bit, which in most cases or in the early stages of the data science life cycle management, where you have less control over how things are done or less of standardization, this model operations loop is kind of least taken into account. And this is one of the most important component that needs to be there as part of the data science life cycle management, where you are delivering maximal value to the organization. And what you are going to notice is that what Habib was talking about earlier in the slide, most of our tools and technologies and people are focused in this delivery bit, in the development bit, and less of focus happens in the operations bit. Now, we have also noticed while we were actually doing this, something that we have noticed is that there are more than developers that are required in this particular setup. So if you look into the roles here, so developers are mostly data engineers, data scientists, machine learning engineers, or DevOps engineers. So they are across all these life cycle. But then there is this very interesting role that exists now, where we are calling them as an auditor, who are responsible for auditing and governing machine learning model that are in production. And then there is this third kind of role, who are the consumers, who are only interested in consuming the model that are getting served in certain way or form. Yep. So any questions until now?
Um, Neil, would you care to explain more about what sort of roles and responsibilities does auditor has?
Yes. So this is something that's there in the later slide. So I will come to that.
Perfect. Thank you.
Yeah. Anything else? Okay, right. So then let's move on. So what we are going to do now is that we are going to look into the development side, and one of the yeah. Um, can you guys hear me well?
I've just put that person on mute.
Can you guys hear me still well?
Yes, we can hear you.
Yeah. Okay. So what we are going to do is that we are going to see one of the most interesting thing that we as developers of data science product get into when we are in this development mode. So when we are in this development mode, so we are keeping the operations aside and we are in the development mode, right? So one of the most interesting story about the model development and how the accuracy or the performance of the most optimal model is not always the most optimal in terms of giving business value is the Netflix prize. So Netflix prize was announced by Netflix in 2006, where they said that we would open up a challenge of $1 million, where the best team is going to get $1 million, and we would want them to create a recommendation engine that outperforms our existing recommendation engine. And there was this 3 years worth of Netflix challenge that ran between 2006 and 2009, where multiple data science teams worked together in terms of improving Netflix's recommendation capability. And at the end of 3 years, the best model that existed increased the root mean squared error on the recommendation engine by 10%, which was great. And then they took away that $1 million worth of money. Now, after that, when Netflix started their work on productionizing that particular model, they realized that the amount of cost that they need to, so the amount of money or the revenue that they need to spend to operationalize the best model is not worth even operationalizing it, right? And hence what happened was that so right at the point where it was going into operationalization, because of the kind of great push of increasing optimality in terms of accuracy, they actually ignored the amount of effort that will be required for it to put it into production. So the operational need that is getting created, or the technical debt that are getting generated by these kind of projects. So the takeaway from that is the fact that when we think about optimizing as a process of training a model and improving on the performance of it, it's not always the case that it adds maximal business value. And in that regard, something quite interesting in this particular example is you can see one example that kind of RapidMiner presented in terms of how, when we look into accuracy as one of the measures of success, in terms of optimizing what our best model is, it's not always the case, right? For example, you kind of look into a particular, so they were solving a churn prediction problem, and then they had multiple models that and they had multiple evaluation criteria, but what they were using as metric of success was a classification error. And you can see deep learning had higher classification error than naive Bayes. And if we choose one particular metric, we are going to choose that metric and constantly will try to optimize that particular metric. And in a lot of cases, we ignore other metrics. Like that's one thing. So here you can see, even though classification error is higher in deep learning, in terms of the cumulative gain that you get in terms of revenue is almost 2 times higher than naive Bayes when you think of a cost sensitive learning. So if you assign a cost to churn and no churn, when you look into classification error, you are looking at classification error as a combined cost consisting of churn and churn, but you are only interested in churn, right? So finding the right measure is important. But one other thing that's extremely important is not to go into this forever loop or iterations of trying to optimize minuscule amount of performance increase, because that might not add too much of a business value. And in that regard, what is important is to create resilient models. And the best model is the one that will hold up in production and will perform well on variety of different test sets. Whatever be the case, when we are developing, we are working on simulations. So we can create many test sets. We can create k-fold cross-validation, but still it is some form of simulation. So putting model into production is extremely important. Now, in terms of what should be the KPIs for a resilient model. So I mean, like there are some great examples. So smaller standard deviations in a cross-validation run, which is a tick for model development phase. You can follow that. Less discrepancy between error rates of test and validation data set. That is still a tick for development phase. But then comes similar error rates for longer time in production model. That basically means when the model is in production over time, how does it keep up with error rates, right? Which you can't test out when you are just in a development phase. The fourth interesting thing is that how much model is impacted by input data drift, which is an extremely interesting subject area. So over time, there is a model degradation, and some of the best models are the models that react to changes in data, but not too sensitive, so that if the distribution changes significantly, it degrades. So good models should be able to handle data drift that happens at the back end, and they should be independent of that. And in a lot of cases, when model does not go into production, you are never checking drifts and the impact of drift over time. Yep. So now that we have talked a bit about data science lifecycle and some of the reason why we should move models much quicker into production, let's come to the machine learning operations phase. Um, Now, machine learning operations, right? When we hear the word operations and when we hear about machine learning operations, first thing that comes to our mind where operations has been really successful is software development. And software development is a particular place where you can actually find a lot of similarity in terms of how machine learning products are built. At the end of the day, the deliverable is a piece of software that goes into production, but there are some key differences in terms of machine learning systems and your traditional software systems. And in that regard, so first important point is development, right? So one of the things that we were talking about was machine learning is experimental in nature. And the challenge is tracking what worked, what didn't work, and to be able to maintain reproducibility while maximizing code reusability. So if you compare it with your typical software development, if you are asked to build a red button, there are probably one or two ways of building a red button. But if you are asked to build a churn model, there are hundreds of ways you can build churn models where you can change your data, you can change your code, you can change your hyperparameters, you can change your environment or the environment on top of it runs, and things change. So if you change one small thing, it changes everything. So that experimental nature of, I mean, there is a stage in machine learning development where experimentation is extremely critical, and there needs to be a place for experimentation, even though if you live in a software development environment. The second key difference is when it comes to testing. The key difference of testing software development systems from machine learning system is machine learning system requires more involved testing than software system. So in your typical software system, you would require to test your code, test your application, and that's it. Whereas when it comes to testing machine learning system, you have to test the quality of the data that comes in. You have to test the quality of the code that's being written. You have to test the quality of the model that gets generated, and also the application. Any question? Anything? No. Okay. And then the third very interesting thing is which is really interesting to think about. So when we write typical software, which is essentially a piece of code that gets packaged and deployed as an application, uh, if nothing else changes, softwares do not degrade over time. So you don't see a degradation characteristic in software. So if you have written a code, there is a very deterministic way you can say that the application works or does not work. Whereas when it comes to models has a decaying characteristic over time, where the same code has generated a particular model, but when the model is in production that's delivering value, the model itself can decay based on the changes in the distribution of the data over time. Which brings a very interesting characteristic in terms of your typical CI/CD framework. Here, you kind of bring in a particular component called continuous monitoring, which is very, very unique to machine learning system. And you also bring in a particular component called continuous training, which is also very, very typical to machine learning systems. So instead of having continuous integration and continuous deployment, now you have continuous integration, continuous deployment, continuous monitoring, and continuous training. So any questions until now on this?
Can you elaborate a little bit more on what does continuous training mean?
Yes, so I will go next into like exactly into that.
Okay, thank you.
Yeah. Okay, let's move on then. Now coming into machine learning operational maturity. Now what we saw was, so this is from Google. So I mean, like we have not come up with this particular framework or architecture. This exists in the internet, and how it is. So machine learning operation is looked into is that there is a basic form of machine learning operations, and then there is a much more matured form or kind of advanced form of machine learning operation. So let me come to very basic form of machine learning operations. In a very basic form of machine learning operations, what you have is you have the data science community or data scientists, data engineers, or the developers who work during the development life cycle. They are working on offline data extracts, and they are constantly working on extracting data, analyzing it, and they go into this experimentation phase where they are preparing data, training the model, evaluating and validating the model. And these are independent steps. Typically, what we have observed is that these are implemented disjointly on something like Jupyter notebooks, where you can do rapid development. And one needs to sequentially manually execute each of these components for it to be able to generate a model out of it. And once you have a good model out of it, what happens is that the model object comes out and it is being stored somewhere. Let's call it as model registry. I mean, like you can think of a simplest form of model registry being a shared folder where the model object exists. But there are much more intricate form of model registry. But the whole idea is that developer is pushing the model into production by putting it into a model registry. And that's where the operations people comes in, where machine learning operations engineers will come in and they will take up the model object and they will wrap it up in an API, and they will make it ready for prediction service to act on it. Yeah. So what happens in this particular scenario is that you have a developer. I mean, like there is a development phase, there is an operations phase, and then there is a production phase in the right at the bottom. And then you have the handover happens in terms of models being transferred from developers to the operations people. Now, some of the interesting characteristic of this kind of machine learning operations is that, first of all, it is manual, script driven, and interactive, right? So this particular experimentation step is really manual. It is script driven and interactive in nature. Something that's also really, really interesting is that there is a disconnection between machine learning development and operations. So what I mean by that is that the process separates the data scientist who creates the model and engineers who are serving the model as a prediction service. So the data scientist is handing over the training model as an artifact, and the engineering team is deploying it into their API infrastructure. Now, where it works really well is when you have a really infrequent release iterations. What I mean by that is that this particular process assumes that the data science team manages very few models, and the model itself does not change over time that much. And what I mean by does not change over time that much means there are two kinds of changes that can happen over time. One is either you can change the model implementation over time. So over time, you can add or remove different features. You can apply different modeling algorithms, and that means making changes to your code. And that is one kind of change. And the second kind of change is that you can keep the same code, but if it works on updated data, so it can be trained by data using the same code, which also generates a new model every time. So there are these two different categories of changes that can happen. Now, in this particular framework, it just assumes none of those changes actually happen. Yeah. Now, let's go to the bit more advanced one. Now, if we look into the advanced one and look at it slightly carefully, so the first thing that we see that came about here is something called feature store. Now, feature store is really, really interesting. Now, earlier in the earlier picture, you saw you had an offline data extract, which data scientist always works on, whereas here comes a particular product, which is called a feature store, that has three different forms of data extraction mechanism. One is this bit where data scientist or the data development team is creating models manually from the feature store. That means these are manual batch extracts that are mostly getting created training data. That's one. Then there is a component that's here where the feature store also serves data for the prediction service that might work in a much more real-time fashion than training. So it requires an online component to it. So it's not necessarily offline. And then there are also components where it feeds into automated pipeline. That means it's not always that there is a human consumption from the feature store, but there are service consumption from the feature store as well. Now, second interesting change that you see here is that instead of having that manual setup, now you have an orchestrated experiment. Now, what I mean by orchestrated experiment is an experimentation setup where instead of running those separate Jupyter notebook, instead of running separate Jupyter notebooks, you are transforming it into scripts. And you are connecting those scripts together where data scientists are changing those individual components. And it's an orchestrated experiment. And that automatically means that there are source code repository that is required where all these changes are presented. And you can also have a CI pipeline, which automatically packages that particular source code repository and packages it together and deploys it as an automated pipeline. And this is where that continuous training piece comes into perspective. Now you see, as opposed to earlier where data scientist was deploying the model asset itself in production, now the data scientist pushing the orchestrated experiment into the source repository, and it automatically deploys a pipeline that generates the model. This means that data scientists or the data development team are not directly deploying model objects, but they are deploying pipelines, automated pipelines, which generates models. And what this enables is that you can create automated pipelines that can continuously train your system without any intervention coming from a data scientist. So you can have a scenario where your predictive service performs some form of continuous monitoring in terms of data drift. And when the data drift goes beyond the threshold, it actually triggers an automated pipeline. And this is what we mean by continuous training. Now, in terms of, there are implementations where, I don't think I'm going to have enough time today for me to show you an example of that, but later on I can definitely send you around some content in terms of how you can implement some of these architectures. Now, How is it different from continuous X? And we had already discussed about this. So CI is no longer about testing and validating codes and component, but also testing and validating data schemas and models. CD is no longer about single software package as a service, but a system that should automatically deploy another service, which is the prediction service. Now you have a new component called continuous training, which is a new property unique to machine learning system that concerns like automatically retraining and serving the models. Now, touching very quickly on analytics and governance. Now, where analytics and governance comes in is mainly when you have systems that are running in production. And I'm going to demonstrate you briefly some of the components that I'm talking about. But the main questions that an auditor or like an analytics governance person ask are things like this, right? So what are the models that are in production? Is there documentation that's there for each of the model? Who has built it? When was it last built? How was it built? What was the mechanism that someone used to build it? What are the different properties of the model? What algorithm did you use? What hyperparameters? What performances? Is it explainable? Is there fairness in it? And an auditor should be able to review all these components for any model that goes into production. And it's not just in production, but there are cases where an auditor can go into the development phase and look into experiments that has been run to come to a production model as well. I might show you some example if I have time. Now, coming to Spark New Zealand's machine learning operations phases. Now, when we started with our data science journey, we were in machine learning phase 0, where the concept of machine learning operations or data science lifecycle management didn't exist, where individual data scientists were building prototype models and they were trying to show the key stakeholders the business value out of it. And when the business value came, the requirement increased. That means we needed to run machine learning models much more efficiently in production. And in that way, we went into this data science lifecycle maturity setup where we first of all stayed in the basic phase. And the basic phase was where we kind of tried to bring in these different components. We wanted to bring in collaboration where multiple personnel, they can be data engineer, data scientists, business analysts, stakeholders, they can come together and collaborate in some way or form in terms of solving the problem. We wanted to bring in experiment and model management as part of it. We wanted to bring in code management, environment management, and governance. Our infrastructure was mostly on-premise. So for collaboration, we use tools like GitLab and MLflow. MLflow were used for experiment and model management. Code management, we use GitLab repository. Interestingly, we did environment management, which is essentially Python infrastructure, building Python environment via GitLab CI. And we also did governance via MLflow. What we noticed is that in this period, the upskilling requirement was extremely high because most of the people who were working in this particular development phase did not have too much of an experience in terms of using all these tools that enables all these things. That means the amount of upskilling that was required was extremely high. And at this point in time, 100% of the models that runs in Spark are definitely in this particular phase. So all these components exist in all of them. Then now we are slowly moving into the more advanced phase where we are trying to integrate the continuous training, cloud migration, and different CI, CD, and CD. And as part of that, we are also moving into Azure so that our overall capability to do all these increases. So we have now gotten into a phase where we are starting to use Azure DevOps and Azure ML. The upskilling requirement right now is low because people have already upskilled in most of the things that they would need to do when they are actually doing things here. So right now it is low. So we are at the very initial phase of this advanced machine learning operations phase. Now, I will now very quickly go into the demonstration. So before that, any questions? Righty-ho. So let me go then into one of the demonstration where I will show you MLflow as one of the tools that exists in the market, which allows us to do some of the things that we were talking about in terms of the data science lifecycle management. People who do not know about MLflow, it is an open source platform for machine learning data science lifecycle management. It has 6,500 stars in GitHub and in active development, so it is a relatively good product. It's made up of 4 components, and I will probably be showing you 2 of the components. So there is tracking and model registry is what I'm going to show you. And if you are interested in architecture, I'll go into more detail later on. I'm not touching upon this at this point in time, but let's just go into looking at how it looks. So here is what MLflow looks like. Now, before I come into MLflow components, I just wanted to mention that MLflow provides you capability to interact with it using many different ways. You can use REST APIs, you can use Python APIs, you can use Scala APIs, and so on and so forth. And Databricks has developed it, so it integrates really nicely with any kind of Apache environment as well. So if you have a Spark cluster, works really nicely with that, and it has great integration if you're on Databricks. Now, what you are seeing here is the MLflow UI for the open source product that they have. And this is one of the product that they're calling as experiment management. And this is what they envision that data scientists are going to use during their experimentation phase. So this targets the experimentation and not the operations. Now, when you look into experimentation, each of the row that you see here is an experiment, and an experiment is typically defined by anything that generates a model as an output. Now, so the whole idea is that you can change your data, you can change your model parameters, you can change your model algorithms, but as long as the end product is a model object, it is an experiment. So you will see that I have one of the projects where we are let's say working on Titanic survival problem, and the data scientist has logged in multiple different experiments. And when now we go into one of the experiment, the interesting, I mean, like, there are certain interesting characteristic that we are going to see. So what it has logged in is when someone has logged an experiment, how much time it took, what was the source file from which it was generated, who had run the experiment, and so on. It has a parameters component where you can specify the specific machine learning algorithm related parameter. These are key value pairs, so these can be anything. Mostly these are algorithms and hyperparameters that you want to log in. It has metrics of success. So when you have a model that needs to go into production, the first thing that you look into are some numbers that tells you how good it is. So you can log in certain kind of metrics of success, which is there. But what is also interesting is that apart from numbers being the metrics of success, we look into other characteristics, what we call as an artifact, to decide if a model is good or not. And this is what they're calling as artifact. An artifact can be anything. They can be an image, which is an AUC, which a data scientist might look into in terms of deciding how good something is. Cumulative gains, lift. So anything that can be created as a file can be logged in. And this is what I mean by when you are creating models, you are not only creating a model object, but you are also creating metadata on top of it, which tells you how good that particular model is, because that's extremely important to capture, because when it goes into production, you have full reproducibility to know what those were when you put it into production. So 1 year later, when you come back to this model, which was in production, you know everything about it. Yeah, so that's experimentation. So once you have experimentation and you have a model available as part of that, what you can do is that there is the second component called model registry. And model registry is a phase where once you have done multiple experiments with multiple that has generated multiple models, then you can choose one of the best model and can deploy it into production. And in terms of MLflow provides something called model registry, which let me first show you how you put model into production. So if you have models available, you go and say register model. And when you say register model, you can choose where it gets deployed. And it just goes and gets deployed. And once you deploy a model into production, let me show what happens over there. Here you go. So here is a model that's in production, and you see that now you have much more model management capability. And when you have this model management capability, you have versionings of the model available. You can go into individual models and look into different characteristics of the model. Like it is connected to the source run that generated that model. So I can click through it and go to the experiment that had ran it, so I know where it is. It has something called stages, where you can transition things into staging or production, which helps a lot in terms of continuous deployment. So you can create automated pipeline that just picks up this tag and always creates a serving component that is on top of a model in production. So that's quite interesting. Where are we right now? So how are we doing with time?
So we've got 2 more minutes left, but
Yeah.
if everyone's okay, we can run over. But is there any questions?
Yeah. So I mean, like, I would much rather take questions now, because most of the thing that I had to tell, I have.
Yes, I have a question. It's about the orchestrated experiments. I wanted to understand why do we have some code in the orchestrated experiments and another piece of code in the pipeline? Is it the same? Are we?
So like I didn't get you. What are you talking about around orchestrated experiments? Sorry, I think
I
my.
think you mentioned that. Was it orchestrated experiment?
Yes, I did. So which is
Yeah.
let me go to that. So that was this bit.
So Neil, what
Yeah.
Claude is asking that why are there 2 source code pipelines, for one for orchestrated experiment and the other one for the main one, right, Claude?
Yeah. Is it the same code, and why is it different?
So you are talking about the source code and the source repository, is it?
Yeah, about orchestrated experiment and automated pipeline. I try to understand the link between those two.
So link between the orchestrated experiment and this pipeline, right?
Yeah, because you say that
Yeah,
the
yeah, yeah.
data scientist creates the orchestrated experiments.
Sure.
And then it deploys the pipeline, but is it the same code? Like, I try to understand.
Yeah, exactly. So what happens is that, think about if you have used Git, you can think of these being your dev branch and the prod branch, right? So in the dev branch, what you do is that you run orchestrated experiment where you test out how good a particular model is, and your development happens in the dev branch of the orchestrated experiment. But when you are really happy with it, you can push it into prod. What happens when you push it into prod is that it takes the orchestrated experiment that you have created and deploys the whole source code itself in the prod, which creates the pipeline. So from source code perspective, when you are developing, you can develop in your own speed, and you can develop multiple times when you are in the dev branch. But once you're happy with it, once you push it into prod, this CI/CD pipeline takes your orchestrated experiment that you have created and takes it as an automated pipeline. So this is nothing but your prod branch. This is your dev branch.
Okay, I see. Right. So we end up with the code developed by the data scientist in production.
Yes, that's correct.
I see. All right. Thank you.
Any other questions?
Sorry, guys, I have to run. Is the recording going to be made available?
Yes, I can make that available in the coming days.
Okay. Thank you, Akash. Thank you, guys. Lovely talk.
Thanks.
Thanks, Priya.
I had a question. So trying to understand, so the strategy from you guys is to use open source tools like MLflow on-prem for experimentation, correct me if I'm wrong, and then the strategy for production solutions to be using Azure, correct me? Is that sort of the approach? So use open source to reduce cost? Is that the strategy, or is there other reasons behind it?
So there are 2 questions. One, I will let Habib answer around open source strategy and the cost. But the other question that you asked around right now, if our strategy is on-prem and then for production, we are thinking about cloud or not. So yes, so right now, our next goal is to move into cloud. But first, we want to move the production bit into cloud. But our strategy is not to keep the development bit on-prem as well. So our goal is to move our development bit into cloud as well. So we want to make use of all the compute capabilities that are available in the cloud as part of something like Azure Machine Learning. But right now, first thing that we need to do is that put the production bit into cloud. Yeah, Habib, do you want to take the open source?
Yeah, Kash, yeah. So I think with regards to open source, our strategy there was that can we get, we want to be more flexible. We didn't want to be tied down to any proprietary software so that it becomes much more difficult for us to move away from it. So that's why our main strategy for open source was, is there something, we'll say, that is very, that we can move on to other places as well as we move from on-prem towards the cloud over there. Now, in the long run, to be honest, ML Flow is a good option, but another good option is Azure ML as well, which is also kind of very cheap for us because anyways we will be working on the Azure platform, which is our preferred platform for our cloud service provider. So that's why I would say there'll be a balance between both in some cases. Either we'll move a lot of the things to ML Flow and keep it over there, or we can also move it to Azure ML as well. But both are very tightly integrated with each other as well. So it should, moving over there shouldn't be much of an issue for us.
Habib, was this a conscious decision to take Azure as a cloud platform, or I mean, it could be? I mean, what's your take on platforms?
That is a much more longer discussion. I can probably talk on that later. But Azure is our preferred platform, would say, for the data and automation within Spark. Yeah.
Yeah, cool.
Just a question on the on that sort of experiment to production kind of flow. Often when you're doing sort of machine learning experimentation, you end up with models that work kind of fine in the experimental domain, particularly with offline data, but aren't particularly performant when they end up in production. Do you end up deploying straight to production from that experiment flow, or do you sort of have like a performance optimization stage as well?
So that's, I think, what Neil would say was also might be talking about is that normally you can have an auditor role as well. So currently there are 3 roles over there, which is production and development and archived. You can also add another 4th role, which is more of an auditing role that, okay, it's currently under consideration. So what we envision for the future is that many people will be working on multiple models, but we need to audit those models from other data scientists in the group as well, and then we'll say push it into production. So there will be an auditing phase, and once the auditor, who might be a fellow data scientist, will actually look into it and then say, yep, it seems fine, all the the performance seems fine based on the objectives that have been defined over there, and then they will move it into production for that one.
Okay, I guess it wasn't really meaning performance from sort of an accuracy perspective, more performance from sort of an operation perspective, you know, time to run and resource usage and cost to run and things like that.
That also, I would say, can be measured. That can be also added as parameters over there as well. So in the experimentation, you can also add parameters. How much time does it take to actually predict one row or a batch row and so on, and then add it as parameters for your selection.
And that becomes extremely critical when you get into a very real-time online setup.
Guys, got another quick question from my end. How do you guys manage coding languages? Because it kind of becomes a religion for, you know, Python, Java, Scala, R. How do you guys manage that in this MLOps cycle in Spark?
Yeah. So interestingly, right now, the data science community that we have in Spark mostly belongs to the R and the Python community. And what we do is that right now we internally, as part of our on-premise system, we support both. There are sometimes requirement for Scala where you are trying to run something like Apache Spark or Spark related code. Those needs to be supported, but it is very specific to the platform on top of which you are running. So right now, what we do is that we actually support Python and R completely.
Got it. Okay. So support both camps and Scala, because you guys are using Apache Spark. Any reason?
So that's mostly around the data engineering bit. So not the data science component. So Scala is mostly used by data engineers who are trying to create data pipeline on top of Apache Spark, and they use a lot of Java over there as well. But we don't touch it. But there are capabilities within our on-premise cluster to kind of support Java and Scala as well. But from a data science community perspective, we are quite restrictive to kind of Python and R right now.
Neil, can I ask you a quick question?
Yeah, sure.
I'm just wondering. I hope you might be able to help me out here. Like when I talk to people in the business, I hear a lot, depending on the data problem that they're trying to solve or the business problem that they're trying to solve, they use either R or Python or Scala or yeah, as a course, nicely said, whatever religion that might be that they're using. Is that still up to date, or is Python something that you nowadays can use for probably every data solution?
I mean, Python is something I kind of personally prefer, and every solution that's possible in the world until now, I have never been I have never got into a situation where I need an integration. I have an integration requirement and Python does not work. So if you ask me at this point in time, if I have to create data science product, if I am given just one choice, what it will be, it's always Python for me, because it has a massive community around it. Two, it integrates really well with other systems. Three, if you look into cloud infrastructures, mostly they support Python really well. So you always have APIs coming out in form of REST APIs, but you'll always have a Python API around it as well.
Yeah, and I'll just add one more thing over there. What we've also noticed is that a few of our colleagues who were earlier working in R and R modeling, they have actually quite adopted to Python a lot. They have started loving it a lot because of all the support around it and all, as Neil mentioned, the big community around it. So people who are actually working in R, for them moving into Python is not a big, what to say, shift. For them, what to say, if they want to start building something in Python, they can still do it, what to say, within a week. They can start building models over there with the right support and the right guidance over there. But at the same time, we also believe that R is also quite a good language as well. And if people want to continue on that, those are the best options that we can provide overall.
Awesome.
And widely
Thank
used as well.
you, guys. Cool.
Any other questions? Cool. I think that's it. So Neil, Habib, from everyone, big thank you. That was a really good session. I learned quite a lot actually. And if you guys do have any questions for both of Neil or Habib, I believe the PowerPoint pack's got your email addresses on the first
Yes, it does.
page.
It
Correct me if
does.
I'm wrong.
What I can also do is that I can send around the PowerPoint presentation with some additional resources that I didn't get too much of a chance to talk about. I'll probably also send around Microsoft version of this particular implementation that I was talking about, advanced machine learning operations, you using Azure DevOps and Azure ML, which you can get started within probably 20 minutes. So I will send you around some of the resources along with the PowerPoint presentation as well today. Yeah.
Perfect. Thank you for that, Neil. And we'll wrap it up there. And hopefully in the next Data Ops meetup, we can meet in person since hopefully we don't go into lockdown again. But yeah, thank you, everyone. And we'll see you next time.
Thank you, guys.
See you guys.
Thanks, Akash. Thanks,
Thank
everyone.
you.
Thanks.
Really appreciate it. Cheers.
Yep. Cheers. Bye.
So
Bye.
cheers. Bye.